Well, in the last class, we are considering parallelization. Of course, we started with this that if there is suppose some job which requires some time, say capital T, there is this critical path is capital T, and you make parallel copies, j number of parallel copies, then by properly parallelizing, which is called unfolding, your input output speed can go up by a factor of j, that is input clock period and output clock period will go down by a factor of j, okay. But hardware goes up also by a factor of j. Then we said that if the process is nothing but an FIR filter, then using some DSP tricks, particularly using something called polyphase decomposition of sequences, we can restrict this increase in hardware somewhat. That is, it will not go up by a factor of j, but it will of course go up, but by a factor less than j. So, for that I consider two parallel structures, that is j equal to 2, that is it was unfolded by 2, and we brought in also then polyphase decomposition of factor of 2. That was one example, but if you want to have further improvement here, that is if you want to see that you parallelize it further, okay, to make it still faster, we will consider another example, that is j equal to 3, that is 3 parallel. Okay. And obviously, we will consider polyphase by a factor of 3. For if it is 3 parallel, it will be 3. If it is 4 parallel, it will be 4, like that. We all know what is polyphase decomposition of a sequence, but quickly, if it is a factor of 3, we can do a quick recap. Suppose we have a sequence like this, suppose x of 0, then x of 1, x of 2, x of 3, x of 4, there is 0, 1, 2, 3, 4, x of 5, x of 8, dot dot dot. If you take fellow, this guy, then throw away the 2 intermediate samples, take this guy, okay. And again, so 0, then 3, then 6, 9, like that. So, you get basically a decimated version, decimated by a factor 3. You get a sequence x 0, followed by x 3, followed by x 6, followed by x 9, dot 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 from this side. If you go to the left hand side, it will be x minus 3 and so on and so forth. This will be called the 0th polyphase factor, that is capital A 0 n, dot 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 dot, which is the 0th polyphase factor x 0 n, and its Z transform is x 0 z. Then if you take this guy 1, then go ahead by 3 4, then go ahead by 3 7 and put them side by side, okay, x 1. Let me put a notch here to indicate this is time origin. So, again notch time origin, x 4, x 7, x 10, like that. This will be called x 1 n. This is the first polyphase factor. If I plug in the zeros, that is if I plug in 2 zeros in between x 0, x 3, again 2 zeros between x 3 and x 6 and so on and so forth, then it will be, its Z transfer will be capital X 0 z to the power 3. That is capital X 0 z to the power m means between every pair of samples m minus 1 zeros. So, if it is z to the power 3, between every pair of samples 2 zeros, that is here 0, here 0, x of 0, x of 3. Then again here 0, here 0, x of 6, here 0, here 0, then x of 9, so on and so forth. Similarly here, but at the moment I am not considering the zeros. So, low clock rate sequence, where after x 0th sample I have x 3. So, this much is the sampling period 0 to 3, 3 to 6 likewise, or 1 to 4, 4 to 7, okay, low rate sequence. The theory for all this had been done earlier, this is just a quick recap. And the last one is x 2 start at 2, go ahead by 3, 5, 8 and like that, x 2, x 5, x. This is the second. If Z transform is x to Z. Obviously, using this we can reconstruct the original one. First plug in the two zeros here. So, after x 0 you have got two zeros, then x 3, then two zeros, then x 6 and like that. The corresponding Z transform will be x 0 Z to the power 3. There is 3 minus 1 two zeros between every pair of samples. Every pair of samples means between x 0 and x 3 there will be two zeros, between x 3 to x 6 two zeros. So, 0 here, x 3, 0 here, x 6 like that. Then here also plug here between x 1 to x 4 two zeros, between x 4 to x 7 two zeros, x 7 to x 8 two zeros. So, that will be x 1 Z to the power 3, then you shift it to the right by 1. So, that x 1 comes at this position, right now it is at origin, x 1 comes here two zeros, then x 4 comes here. So, they come in their respective places, x 1 comes back to its original place, x 4 comes back to its original place, x 7 comes back to its original place, okay. And then in between them two zeros and you add them. All the theory for this was explained in the previous class, and again here also put in two zeros between x 2 and x 5, between x 5 to x 8, between x 8 to x 11 and shift them by 2. So, x 2 which is at origin now, it will come at position number 2 and so on and so forth. So, everybody will be coming into their respective position, shifting by 2. This is your x z. When you get back your original sequence, Z transform x z is this. Okay. This is the factor of 3 polyphase decomposition. We will use it for 3 parallel FIR filters. That is, when you are unfolding a FIR filter by a factor of 3, we will make clever use of a polyphase decomposition by a factor of 3. So, that hardware does not go up by 3, but by a factor less than 3, quite less than 3. Okay, this is what we are going to do. So, you basically have an FIR filter whose transfer function is h z, input is x z, which is whose z transform is x z, output y n whose transfer function whose z transform is y z. So, you go for factor of 3 polyphase decomposition for both h z, x z and y z. So, h z is h 0 z to the power 3 plus z inverse h 1 z to the power 3 plus z inverse to h 2 z to the power 3. X z x 0 z to the power 3 plus z inverse x 1 z to the power 3 plus z inverse to x 2 z to the power 3. Okay. If I multiply the two, I will get y z, and y z should be of the form that is, when I multiply the two, first find out a polynomial in terms of z to the power 3 only, that under this. Then find out terms from which z inverse can be taken common, and remaining part is again a function of z to the power 3. That whole thing will come here. Then out of the remaining terms, z to the power minus 2 should be common, and remaining fellows should be a function of z to the power 3 again. So, they will come here. Thereby, I know I will find out what is y 0 z to the power 3, what is y 1 z to the power 3, what is y 2 z to the power 3. If I multiply h z and x z, I will get like this. let me write Hz as H0 z to the power 3 plus let me take z inverse common here. So, remaining part let me say V z to the power 3 or not V, I have a notation for this. Z inverse I will call it W z to the power 3, where this is nothing, where W z to the power 3 if I take Z inverse common, it will be H1 z to the power 3 plus Z inverse H2 z to the power 3. Okay. Now, one thing, I have been having this bracket z to the power 3 coming everywhere, and it is kind of making things very congested. So, for the time being I might just drop it, I might call it H0, I might call it W. H0 means H0 as a function of z to the power 3, W means W as a function of z to the power 3, Y0 means Y0 as a function of z to the power 3. Okay, because every time if I write H0 then bracket z to the power 3, W bracket z to the power 3, it will become very clumsy. So, taking your permission, I will just drop this. So, I will just write like H0 plus Z inverse W, which is this. All right. Similarly, in Xz, I take X0 common as X0 z to the power 3. Let me straight away write X0, because I told you whenever I write X0 actually I mean X0 bracket z to the power 3. I am just dropping it for the sake of convenience, so that there is no congestion, there is no clumsiness. And again z to the power z inverse, I take the remaining part common, that part is called V, where V means V is equivalent to V z to the power 3, which is actually, if you take this common, okay. So, this is 1, this is 1, Hz is H0 plus Z inverse W, X is X0 plus Z inverse V, and Hz into Xz is Yz, Yz is Y0, you can even write it this way, you can erase this, you can call it Y0, Y1, Y2, means Y0 as a function of z to the power 3, Y1 is a function of z to the power 3, Y2 is a function of z to the power 3, just I am not writing that, okay, it is in our mind. So, H into X is Y, all right. Now, if you do that, I will do that right here. So, Yz will be H into Hz into Xz okay. And if you substitute Hz into Xz, it will be H0 X0, okay, as a function of z to the power 3, then z inverse 1, z inverse 1, okay, the z inverse 2 Wv and the two cross terms, but we will write it in this manner: H0 X0 plus z inverse 2 Wv, and when it comes to cross terms, we will not carry out the product X0W or H0V. We will follow the same trick which we did earlier, that is, we will avoid this multiplication X0W or H0V by introducing more addition. We will just take Z inverse common, take H0 plus W H0 plus W, X0 plus V, and from this subtract this H0 X0 which is already there. So, no need to compute it, and WV which is already there. So, that will give you the cross terms W X0 H0 V, okay, W X0 H0 V with Z inverse common. So, only this product minus this product and this product. Now, H0 X0 already outside, already obtained, WV already obtained. Okay. So, I do not need to recompute this, that is why I am writing in this form. This is the form which I told you is used again and again in this. This is a trick we use to minimize number of multiplications of products. So, this is what I will write, where this is a bit messy, but you can cross check and verify that what I am doing is correct. Now, WV, what is WV? W was, one of them is x1 plus Z inverse x2, okay, that is V, other one is h1 plus Z inverse h2, that is W. This is W, this is V. Okay. This again we write in this way, x1 h1, that is h1 x1, and another term Z inverse 2 h2 x2. But when it comes to cross terms, take the Z inverse common, I will write again in a similar manner, x1 plus x2, h1 plus h2 minus the same h1 x1, same h2 x2. These are already calculated here, so no need to recompute. Okay, so that saves computation like above. This is how I find out WV. So, this WV has to be put in here. If I put in the WV here, what I get is we will just substitute this here. What I get, I write in the fresh page. In fact, I am writing directly from the book by Pari, but it is just a substitution there, nothing conceptual, and just rearrangement of terms. So, what we will get there is this. If you substitute that y will be this bracket ends and this also ends, minus, it is just substitution, but it becomes very basic, not minus, plus Z inverse 1 It is direct substitution only, nothing else. Okay. And then we simplify it, so that we finally, after some simplifications which are given in Paris book, I am not going into that, it is just messy. Finally, everything you can write as y0 plus z inverse 1 y1 plus z inverse 2 y2, okay, where let me write in the next page. So, again I rewrite y is y0 plus z inverse y1, y0 is a function of z to the power 3, y1 is a function of z to the power 3, y2 is a function of z to the power 3, sorry. Okay, where from those messy expressions y0 as a function of z to the power 3 is nothing but, this comes by calculation, is given in Paris book. So, I am not doing this messy algebra. These are all function of z to the power 3. Okay, this is h0 is a function of z to the power 3, x0 is a function of z to the power 3. Actually, this is nothing but a function of z to the power 3. All these are function of z to the power 3. Then y1 as a function of z to the power 3 will be h0 is a function of z to the power 3, h1 is a function of z to the power 3, same everywhere, x0, x1, all. And last one, bit complicated, but you can see one thing, we can now unscramble thing. There is one term h0 x0 present here, h2 x2, h1 x1, h1 x1 comes here also, h0 x2 again comes here, h2 x2 again comes here, h1 x1 comes here, h1 x1 comes here, so on and so forth. So, these terms, though used in many places, we do not have to recalculate again and again. h0 x0 is nothing but passing the polyphase component x0n through a filter h0n. Now, right now what we will do is this, instead of obtaining these as a function of z to the power 3, we will write them as a function of z. Remember, if y0 z to the power 3 means between every pair of samples of this sequence y small y0 n, there will be 2 zeros, that is why it is z to the power 3. But suppose we consider only y0 n, whose z transform is now y0 z. Similarly, y1 n and y2 n, y3 z. So, now it will be everything will be function of just z, not okay, which means what is h0 x0? I will pass the polyphase sequence x0n, small x0n through a filter, FIR filter of impulse response small h0n, okay, which is the 0th polyphase component of the original hn. Similarly, for h1 x1, similarly for h2 x2, whenever you have got these terms h0 plus h1, basically it is the new filter whose impulse response will be what? Summation of the two polyphase components small h0n and small h1n. Okay. Length does not change, the support, that is the position where h0n and h1n located, they remain same, just they get added. So, the new filter, before processing the input, I will take the 0th polyphase component and first polyphase component, add them to create a new sequence, pass it through this filter, so on and so forth. That will be the philosophy, but we will be reusing terms, that is the advantage. For instance, if you see h0 h plus h1 into x0 plus x1, I am sure it will be occurring somewhere, like it is occurring here again. So, I will be doing this calculation only once, though it is occurring twice. Similarly, this term h1 plus h2, which is a filter, it is processing signal x1 plus x2, this will be coming here also. So, I will not be doing it again and again, okay. I will be just taking common, and likewise this will give rise to the simplification. So, this part I will do in the next class, next section. Thank you. বন্ধ করো।